Meow. Hello, viewers. Good morning. Good morning. I'm gonna wait for us to have at least 25 viewers before I get started. Yes, because you may do attendance. This class starts at 10:25, so anytime after 10:20, you can submit attendance. Hello? Waiting for 25 concurrent viewers before I get started. Waiting for 25 viewers, waiting for a few more people to join us. It was kind of weird. Last class period, I had 48 viewers. And the class has like 35 people in it, so I was a little bit confused. Like, who are those extra viewers? All right, we're at 25 concurrent viewers. So what we're going to do today, we are going to learn, today's lesson is just a little bit beyond what we learned last time. So we're going to continue to talk about velocity time graphs. And then we're just going to do a number of problems just to get some practice. Okay. So there's a concept that I need to introduce to you guys, and that is a concept called area under the curve. Okay, so I'm going to draw a graph. And when you're doing area under the curve, it's really important that you know where the horizontal axis is. Okay, so here's the horizontal axis. And then I just draw a graph. Maybe it looks like this, does a couple of these, like that. Okay, so the area under the curve is the area of the space between the horizontal axis and the graph. Okay, so here's the horizontal axis, here's the graph. So the area between the two would be the area of this space. Okay, the area of that space. And then if the graph dips below the horizontal axis, then we don't shade below. It's not just shade below, it's shade between the horizontal axis and the graph. So in this case, we would shade that area. So the area under the curve is the area of that space. And then once it goes above, we again shade down, and once it goes below, we shade in below. Okay. There's another thing that we have to be careful about, and that is that if the area is above the horizontal axis, it counts as positive. Okay. And if the area is below the horizontal axis, it counts as negative. Okay. So the area, you can have a negative area if it's below the horizontal axis. So this is the concept of area under the curve, measuring the square footage of the space between the graph and the horizontal axis. Now, if you have a wiggly line like this, you would have to use what's called calculus to figure that out, but we're not going to have that in this class. This is not a calculus-based class. So I will give you, when we do the area under the curve, I will always give you things like, line segments. So for example, if it were something like this, you could think about this area under the curve as the area of this triangle, okay, plus the area of this rectangle, plus the area of that triangle, minus the area of this triangle. So we can think about it as a sum of the areas of simple shapes, okay? So there's no knowledge of calculus really required. You just need to know what is the area under the curve, and this is how you visualize it, okay? So what does it mean, okay? So let's try to interpret area under the curve. Well, what if we have a velocity time graph? Okay, so here's a velocity time graph. And this velocity time graph is, let's draw a velocity time graph for something that's moving in the positive direction and it has a constant velocity. So that would look like this. All right, so this is a velocity time graph. We can see that the velocity is positive and it's a flat line indicating that the velocity is staying steady, okay? It's the velocity that's staying steady. If this were a position time graph, then this would just represent you were standing still, okay? So this is a velocity time graph. Okay, now what if we calculated the area under the curve for this graph? Well, if we did the area under the curve would just be the area of this rectangle, okay? And the area of a rectangle is base times height. Okay? Now, what is the base? The base is the time elapsed, and the height is from 0 to whatever the velocity was. So the height is just the velocity that you were traveling at. So area in a velocity time graph is velocity times time, okay? But if we use the definition of velocity, velocity is displacement over time. So if we multiply both sides by time, we get velocity times time equals displacement. So, what we get is the area under the curve of a velocity time graph is equal to displacement. Okay? So that is our major new fact for today. The area under a velocity time graph is displacement. Okay? So that's going to lead me to a table. All right, so this table has everything that you need to know about velocity or about motion graphs. First thing you want to look at is you always want to read your axes. And there are two types of motion graphs that we have discussed, which are position time graphs and velocity time graphs. Okay? Position time graphs and velocity time graphs. So for a position time graph, if we want to get the velocity, then the velocity is the slope. Okay? If we want to get the acceleration in a position time graph is bendiness. Okay? And if you want to know the position in a position time graph, you simply read the graph. Okay? If I want to know what is the position at 3 seconds, I would simply go to 3 seconds and read what the position was, okay? If you have a velocity time graph, how do you get the velocity if you're just reading, if you have a velocity time graph? If you want the velocity, you simply read the graph. Okay? There's no calculation required because a velocity time graph tells you the velocity at a certain time, okay? No calculation required. What if you want the acceleration from a velocity time graph? Then you need to calculate the slope. Okay? And lastly, what if you want the displacement? If you want the displacement, then you need to calculate the area under the curve. Okay, so this is everything you need to know about motion graphs that we up to this point. So let's do a couple of examples. So basically, this is the entire lesson for today. You learned all there is about motion graphs, but we're just going to do a couple of examples to solidify your understanding. Okay, so. The first thing I want to work on is describing motion. Describing motion in words. Okay? So what if I have this graph right here? So this is a position time graph. And what if it looks like this? So this is a position. So it has two segments. It has a bendy segment, and then it has a linear segment. Okay. Now, because this is a position time graph, I'm in this left column here when I interpret it. So velocity is slope, acceleration is bendiness, position, I just read the graph. So we can see that what's happening here is we have a portion where we're accelerating. Actually, technically, this would be slowing down because it goes from steep to less steep. So this would be a deceleration, if you will, or a negative acceleration. And then in this second segment, we can see that the graph is now linear. Okay? See? It's linear. Here it's not linear. You can see that it bends above. Okay? So this is a linear segment. And if the graph is linear and it's a position time graph, that means that it's a constant velocity. So this section represents a constant positive velocity. Okay? So that would be an example of interpreting this position time graph in words. What if you had a velocity time graph? And what if that velocity time graph looked something like this? Okay. So for this velocity time graph, we can see that it has basically three sections. It has this section right here. It has this section right here. It has this section up here. Okay? So for this segment, we have a velocity that is negative. Okay? So that means that it is moving back. Okay? And then right here, oh, by the way, it's moving back and it has a constant speed. The reason it's a constant speed is because the velocity is steady. It's negative and it's steady at that negative value. Okay? Here, the velocity is moving away from zero. It's getting further and further from zero. So, all right, it's getting further and further from zero. So that means that we're going faster. Okay? So in this second part, we're moving back and we're speeding up. Okay? And then we have, so there's a very good statement in the live chat, which is what could change the velocity that quickly in that short of amount of time? Yeah, so basically this person or this object really got jerked around because the velocity went from negative to positive just like immediately. So that's like going like that, all of a sudden reversing direction. Okay, so that is not realistic at all, but I just put it in there just because. So what's happening here is we've got a positive velocity and it's steady at that positive value. So this is moving forward, constant velocity, constant speed. Okay? So that is interpreting that in words. But in reality, you can't have a velocity that changes instantaneously. Okay. So let's do an example. Let's suppose we have a velocity time graph. And maybe the velocity time graph looks like this. Okay, so here's zero velocity. Let's say that the velocity goes up to a peak of, let's say, 30 meters per second. And that peak occurs at 13 seconds. And then the graph ends at 20 seconds. So what is happening here? Well, in the first segment, notice how the velocity is positive the entire time. So this is moving forward consistently. In the first part, you are moving forward, and the velocity is going from 0 to 30. So that's getting faster. Okay, so this is speeding up. Here in this section, the velocity goes from 30 back down to 0. So you're slowing down, but notice how the velocity is positive the entire time. So this is moving forward, but slowing down. Okay? So that's how that works. So I like to think about this graph as kind of similar to what you might have if you were traveling between stoplights. Okay, the light turns green. You start out at rest. The light turns green. Okay, the light turns green. You accelerate, pick up speed, and you accelerate, and then the next light is red, so you then have to slow down to a stop. So you're going forward the entire time, but you're speeding up at first and then slowing down as you approach the next stoplight. So this is what I would call a qualitative description of the motion. So qualitative means using words, okay? Quantitative means using numbers. Okay, so now let's give a quantitative description of this motion. All right, so in particular, what is the acceleration at 15 seconds? So 15 seconds into this journey, where is that? Well, we can see that the transition occurs at 13 seconds. 15 seconds is after 13 seconds. So I want the acceleration corresponding to this line segment. So how do I get acceleration if I have a line segment? And it's a velocity time graph. So if I have a velocity time graph, the acceleration is the slope. Okay? So what I'm asking for is the slope of this line segment right here. So we can see that the velocity goes from 30 to 0. So that's a rise of negative 30 meters per second. And this line segment lasts from 13 seconds to 20 seconds. So that is 7 seconds. So the acceleration is negative 30 over 7, which would be, what, 4.28? Negative 4.28 meters per second squared. All right? So that's the acceleration at 15 seconds. What if I asked you, what is the total displacement? Again, I'm looking at the velocity time graph, and if I want displacement, that is area under the curve, okay? Oh, there's a good question of why is it negative 30? It's because this line has a negative slope, so the velocity is going down from 30 to 0, so the change is negative, okay? So total displacement is area under the curve. So what I'm asking for is the area of this region right here, okay? So the total displacement is going to be the area of that triangle. The formula for area of a triangle is 1/2 base height. So that's going to be 1/2. The base of the triangle is from 0 to 20. The height is from 0 to 30. So 1/2 times 20 times 30. So that's going to be 300 meters. So that would correspond to basically the distance, would correspond to the distance between stoplights. All right. What if I asked, what is the velocity at, so this would be the instantaneous velocity. What is the instantaneous velocity at 6.5 seconds? So what if I want to get the velocity from a velocity time graph? Okay. So if I have a velocity time graph and I want to get the velocity, all I have to do is read the graph. Okay. So 6.5 seconds. That is exactly halfway in between 0 and 13. So what I'm asking for is, what is the velocity right there? Okay. And if it's halfway in terms of time, it's going to be halfway in terms of velocity. So this would be 15 meters per second. All right. Cool. So let's do another example. I'm going to do maybe 2 more examples, I think. So for this first example, let's do a position time graph. Okay, position time graph. So position in meters, time in seconds. And let's say it looks like this. I'm going to rotate this just so I can draw my lines easier. That's supposed to be a straight line. Okay, so it's kind of like a ramp. This is coordinate, let's say 50 meters. This is 10 meters. This is 8 seconds. And this is 20 seconds. Okay, so what do we have going on here? This is a position time graph. All right, position time graph. So this is what I'm looking at. Velocity is slope, acceleration is bendiness, position, read the graph. So let's describe it qualitatively in words. If we describe this qualitatively, what's going on here? Well, this is a straight line. And if you have a position time graph that is a straight line, that corresponds to a constant speed, okay? So this is a constant velocity, constant negative velocity. The reason it's a negative velocity is because the slope is negative, okay? And then from 8 to 20 seconds, we have an acceleration. I have not taught you, if you have a position time graph, I have not taught you how to actually numerically calculate the acceleration because that requires calculus. This isn't a calculus-based class, so don't worry about that. You just have to tell me, is it accelerating, yes or no, and when it's a position time graph. If it's a velocity time graph, I will ask you to calculate velocity. All right. So let's go ahead and answer some qualitative questions about this. All right. So what if I asked you, what is the total displacement? There's a question, would it be moving backwards? Yes, it is moving backwards. What is the total displacement for this entire journey? Well, we can see that for this entire journey, we start out at a position of 50 meters, and we end up at a position of 0 meters. Okay? So that means the displacement must have been, if you go from 50 to 0, that's a displacement of negative 50 meters. Okay? 50 meters to 0 meters. What if I asked you, what is the velocity at 7 seconds? So 7 seconds is right about here. And so 7 seconds is underneath this straight line segment. Okay. So if I want velocity and I have a position time graph, I'm calculating the slope. Okay. So I want the slope of this line segment. I can see this line segment goes from 50 down to 10. So that's a rise of negative 40. It's a negative rise because it's going down. And then the run is from 0 to 8 seconds. So the slope is going to be negative 40 meters in 8 seconds, which is going to be negative 5 meters per second. Okay? We'll do one more example and then we'll transition to the Zoom room. So this is AP1 915, period 6, part 2. So one last example here. Let's do another velocity time graph. Okay. Let's suppose that it looks like this. All right. So this graph has too many features, so I'm not going to ask us to describe it qualitatively, but we are going to do some calculations with it. So let me put in some numbers here. So here's velocity 0. This velocity corresponds to negative 40 meters per second. This corresponds to plus 20. This is 5 seconds. This is 12 seconds. This is, say, 15 seconds. And this is, let's make it 18 seconds. So I've given all of the, this graph, I might not have drawn it to scale, but I've given you all the important numbers so that you can calculate areas and slopes and stuff, okay? So first of all, let's calculate. What is the total displacement? So this is a velocity time graph. So total displacement is the area under the curve. Now this area is a little bit complicated because all right, so this, Uh-oh. This area is a little bit complicated. So the way I think about this is I've got this rectangle right here. That's a positive rectangle. Then I've got this triangle right here that's above it's a positive velocity triangle. So there's that triangle. And then I've got this triangle, which is going to be a negative triangle because it's below the horizontal axis. Okay? So I'm going to think about this as rectangle plus triangle minus triangle. So I'm going to literally just write the dimensions on here. So this rectangle has a height of 20, and it has a width that goes from 0 to 5. Okay? This triangle has a height of 20, and it goes from 5 to 12, so that's a width of 7. Okay? And then this last triangle goes from 12 to 18, so that's a base of 6. And it goes from 0 down to negative 40, so that's a height of 40. Okay? So if I use the formula for area of a rectangle, base times height, that's going to be 20 times 5. Area of a triangle, 1/2 base times height. Area of a triangle, 1/2 base times height. Okay? So this is going to be 100 plus 70 minus 120. So that equals what? Plus 50 meters. So this thing, whatever object has a motion graph described by this, would have traveled 50 meters. All right? What if I asked you, what is the acceleration at 13 seconds? So acceleration, if I have a velocity time graph, acceleration is slope. All right? So I want the slope at 13 seconds. 13 seconds is between 12 and 15. So I'm asking, 13 seconds is about right there. So I'm asking for what is the slope of this segment right here. All right? So what is the rise of that segment? Well, it goes from 0 to negative 40. So that's a rise of negative 40 meters per second. And then the run is from 12 to 15. So that's a run of 3 seconds. So my acceleration would be negative 13.3 meters per second squared. All right. I'm going to ask one more question here. Maximum speed. What is the maximum speed in this problem? I'm going to let you guys answer that. I'm going to wait. Type it into the live chat if you know the answer. What is the maximum speed for this entire motion? My live chat is really delayed today. I'm not sure why there's so much delay between. Excellent. Yeah, someone said 40 meters per second. So I can see that this graph goes between plus 20 and negative 40. Okay. Now, even though plus 20 is greater than negative 40 in terms of numbers, speed is looking at the absolute value of that. So 40 meters per second is faster than 20 meters per second. So the max speed is 40 meters per second. So that's my lesson. And so I will meet you on the Zoom chip in the Zoom room. Okay? Toodles.